from the homework, section 2.2, number 12. I'm going to go ahead and write this as a determinant. And I'm going to find the determinant in two different ways. First, I'm going to find it by using row reduction. So here, we find the determinant by row reduction. So I'm going to take this 1 to get a 0 where that negative 2 is. And so this is 2 times row 1 plus row 2. And then also we'll say 5 times row 1 plus row 3. So we get 0 there, negative 6 and 4, negative 2, get a 1 there, 0 here, 5 times row 1 plus row 3. So negative 5, indeed, thank you. So this is 15. Negative 5 times negative 3 is 15, minus 2 is 13. And then negative 5 times 0, 0 plus 2 is just 2. I would like to have a 1 here at A22, so no problem. This is a determinant, so I'm going to factor out a negative 2 from row number 2. Now look at what you have left. This is 0, 1, negative 1/2. 0, 13, and 2. Because obviously, when you multiply that negative 2 back in there, look, this negative 2 represents that here I've done this, I've factored out a common factor out of one row. If you go back to section, I think it was 2.2 in the beginning, we gave 3 principles for row reduction. And the first one was, if you interchange the rows, negate the determinant. If you factor out a common factor from one row, it's that common factor times the determinant, right? If you add a multiple of one row to another row, the determinant does not change. And so now I'm going to use this 1 to get a 0 where that 13 is. So we'd say negative 13 times row 2 plus row 3. That negative 2 stays the same out in the front. 1, negative 3, 0, 0, 1, negative 1/2. This is 0, 0. We have negative 13 times negative 1/2 is 13 over 2 plus 4 over 2. That's 17 over 2. The determinant now, if it's a triangular matrix, is the entries multiplied along the main diagonal times that negative 2. This is negative 2 times 1 times 1 times 17 over 2. We get negative 17. Now, if you're not sure that that's the right answer, I would employ you to solve the determinant by using cofactor expansion to see if the two come out to be the same. On the test, I will have a problem just like this where I will give you a matrix and I will ask you, find the determinant by row reduction. So you have to show me these steps here. But you can, on your own, with that, solve the determinant by using the arrow technique or cofactor expansion just to check to make sure that what you did here with row reduction is indeed correct. You don't want to miss that problem and by some careless mistake where you could have checked it by some other method for finding the determinant to make sure that what you have is indeed legitimate. When the Apostle Paul went and preached in Berea, the Bible says that he didn't get too many amens. But the Bible said that they went and they searched the Old Testament scripture to find out that what he was talking about was so. And then when they verified themselves by looking at the scriptures themselves, then they could agree with them. You never want to take anybody's word, and Daniel's not taking my word. Yes, sir. And so if that's the case, it'll be, if you take out a -2 from row 1 and also from row 2, it'll be -2 to the second power, or 4 times that determinant. Yes, sir. Yep.
So you just multiply those two numbers outside together.
Yes, sir. That's right. And in section 2.3, which we'll get to, there's a theorem that we start off with that talks about how to do that. Okay. So if you take this problem and find the determinant by cofactor expansion, I will, since I have a 0 there, I will use cofactor expansion along the first row. So here, and you remember the signs for the permutations: plus, negative, plus, negative, plus, negative, plus, negative, plus. So here, this is the 1 here, and that sign is positive, and so I delete this row and this column, and so I multiply times the determinant of the submatrix. So this is 4, 1, -2, and 2. And then it's going to be plus here, this -3 times the sign for the permutation change, the -1. And I delete its row and column. So I multiply by the determinant of the submatrix here of the entries that are left: -2, 1, 5, and 2. And so we solve there. This is 8, 4 minus a -2 is 8 plus 2. And this is over here, plus 3 times parentheses -4 minus 5. So we get 10 plus 3 times -9. That's -27 plus 10. That's -17. Was everybody happy with that? Okay. All right. Let's look now at section 2.3, properties of determinants. And we've kind of been talking about it, but let's give the formal justification for it. That the determinant of a matrix where there's a common factor in all 3 rows becomes, if it's a 3 by 3 like this example is here, if I can factor out a k from each row, so that's going to be k to the n, whatever the number of rows you have. And we can only take the determinant of a square matrix anyway, so the number of columns will equal the number of rows. So here I have 3 rows, and this k is common in all 3 rows. This becomes k to the, here, 3rd power times the determinant that's left after you've factored out that scalar k from each entry. Here's an example. Notice that in all of these terms, there's a common factor of a 3. So I take out the 3 from each row. What if you take out a 3 from just one row? Then it's just 3 times that determinant, right? If you take out a 3 from 2 rows, it's 3 to the second times that determinant that remains. But if you take out a common factor from all 3 rows and you have a 3 by 3, it then becomes 3 to the third power times that determinant that remains. Now, property number 2 is important. It says this, that the determinant of the sum is not equal to, the determinant of the sum is not equal to, that's it, the sum of the determinants. I want to get my English right. Do you see that? And that's one of the problems on the true and false as well. And it said that the determinant of A plus B is equal to the determinant of A plus the determinant of B. And the question is true or false. And we say, I don't know, right? Well, let me show you. And if you say it's true, then you got to have justification. That means that there has to be a property, an axiom, a theorem somewhere that you can say, because of this theorem, this guy is true. But if it's false, just give me one counterexample. That's all you need. You remember in that O.J. trial? You know, it was a mockery. It was. But let me tell you how he got off. Because Johnny Cochran, listen to this, he knew mathematics. You know what? You know, when I'm at home or when I'm at church, I don't find myself arguing with people because so many people don't know the principles of mathematics. I do. And because I know that, then I limit what I say. Because in mathematics, there's no argument. I mean, there is an argument, there's an intellectual argument, not a foolish argument. You know, a lot of people engage in foolish arguments in America. This side got to say this side says that. They have no justification based on feeling. You know, there's no mathematical or scientific evidence to say what you're saying, other than you feel like it. It's almost even with the candidates. Because I feel like this, I'm voting for him or her, whatever. But mathematically, do you have justification for what you say? Johnny Cochran knew the principle of mathematics, and here's what he did. He knew that the other side said that O.J. Simpson committed this murder. All Johnny Cochran had to do was to say, no, that's not true. Just give one counterexample that is not true. Well, the other side that accused the man pulled up some gloves that said were used in the murder scene. Blood was on the gloves. And the side that argued that this man is guilty, they said, these are the gloves here. And all Johnny Cochran had to show was that the gloves didn't fit. Whole argument. That's right. You must have quit, right? And the whole argument failed. Wow. Now, you know, those gloves could have been anybody's. But watch this. The side that wanted O.J. to be guilty, they said these are his gloves. Wow. And he just used that counterexample. Just give me one counterexample where it's false. The whole argument fails. Wow. And when I'm at home and when I'm at church and I hear things being said and talked about, and I just give one simple counterexample. I said, look, there's no more argument now. We're done. There's no more argument. And you know, when I was a student, I used to always watch the U.S. Senate debates on the floor of the U.S. Senate. Back then, when you had men like Robert Byrd and George Mitchell from Maine, Strom Thurmond, and Patrick Moynihan, Sam Nunn, Patrick Moynihan from from New York, Sam Nunn from Georgia. These men were students of logic. They were students of rhetoric. They were students of debate. And I don't know what we have now, and I don't even watch it anymore. But man, let me tell you, and often I would get a joy by watching George Mitchell, because, see, he knew that you can be wrong, I can be wrong, but if I just show in your argument one fallacy, then your argument fails. That's all. That's all. And he would do that. He would say, I question your logic. You got to know something about logical reason. You got to know something about the fallacies of logic, right? And he had studied all of the arguments in terms of Platorian and Aristotle, and how they would form logical patterns to get contradictions and all of these inconsistencies in our language. Wow. But now, if you argue with a fool, doesn't matter how good your logic is. The book says that he who argues with a fool is a fool himself. And so that's why a lot of times when I'm engaged in arguments, I just be quiet. Because it doesn't matter what I say, no matter how clear my justification is. If that's a fool that I'm talking with, they've made up their mind, and whatever they're saying, they're going to believe that. And so I just put my hand over my mouth. Okay. So let me show you that this example here, with an example of the reason why this statement is true, and the reason why you don't get equality. So here, let A equal to this matrix and B equals 2. And you can pick whatever examples you want to make it work. You're just showing a counterexample. Now notice that the determinant of A, do you see what that's equal to? 1. The determinant of B is equal to, do you see what that's equal to? 1. What's the determinant of A plus B? It's 0. Do you see that here, that this implies then that the determinant of A plus B cannot equal the determinant of A plus the determinant of B. Here for this example, this local example, how can 0 equal to 1 plus 1? Okay. Just did a counterexample. And I remember on the test, there was one test I gave, and I had this question on there. And there was one student, he gave me an elaborate example, where it was false. But he didn't use my simple, matrices, little a and little b. He had, it was like a 3x3. But indeed, they didn't add up. And I said, oh man, that's cool too, Yeah. I'll try to give it as simple as I can. Property number 3, if A and B are matrices of the same size, then the determinant of A times B is equal to the determinant of A times the determinant of B. I won't waste your time on the proof of this. It's quite extensive. You can look it up if you want, but this is indeed a true statement and is valid for all situations of matrices of the same size. Property 4 is very important. I put the proof here in the notes for you, and this theorem says that if A is invertible, then the determinant of A inverse is equal to 1 over the determinant of A. There is one other property that must be added to the monster theorem, and it says this: I think we have like 6 of them so far. And the next one would be is that the determinant of A is not equal to 0. If the determinant of a matrix is equal to 0, then the inverse does not exist. Look at this theorem right here. This theorem says that the determinant of A inverse is equal to 1 over the determinant of A. But if the determinant of A is equal to 0, you don't get the determinant of A inverse. Matter of fact, you don't even get A inverse itself. Well, the proof of this is very straightforward. You take the fact that A is invertible. If A is invertible, then you know that you have the statement A inverse times A is equal to the identity matrix. Take the determinant of both sides. Use property number 3 up here. So here, if I have A inverse times A is equal to the identity, take the determinant of both sides, I get the determinant of A inverse times A is equal to the determinant of the identity. I use property number 3 to break up the determinant of A inverse times A, which is the determinant of A inverse times the determinant of A. But the determinant of that entity, look, that's a diagonal matrix. So its determinant is equal to 1. So I get the determinant of A inverse times the determinant of A is equal to 1. Just divide both sides by the determinant of A, of which it has to exist, because if it's equal to 0, then I don't get what I'm looking for, and that is I'm looking for the determinant of A inverse is equal to 1 over the determinant of A. If A is not invertible, then you cannot find the inverse, you cannot find the determinant of A. Now, 2 more things in this section. Any questions? I'm sorry. 2 more things in this section, and we're done. There was a student here on this test that I just gave back. They were using the adjoint in the matrix of cofactors to solve some of the problems, and I hadn't covered that. I don't know if they either had this class before or probably had it, like I said, in high school or somewhere else. And so what's one of the purposes for finding the adjoint? One really cool purpose of finding this adjoint of A, whatever it is that you can use it to solve for the inverse of a matrix without row reduction. Remember that process of finding the inverse of the matrix? You put on one side of it the identity matrix, and then you reduce row echelon, and hopefully you end up with each side transposing where the side that you started off with A inverse, you started off with A, and over here you have the identity, and then you use row echelon, row reduction. And so this side that had the matrix A, once you're done, you see the identity matrix, and then over here you see A inverse. If you recall, there's a lot of steps doing that, right? Well, is it possible to find A inverse without going through all those steps? Yes, it is. And one way is to first find the matrix of cofactors. So if you got a square matrix, some n by n matrix, find for each entry, find its cofactor. And then when you found the matrix of cofactors, transpose it. The transpose of this matrix is called the adjoint. Even in the English, that word is not so, right? But in mathematics it is. So this adjoint of A, which we denote by ADG parentheses capital A, is useful to finding the inverse of a matrix A. Yes. And then later on we'll find out how can you solve a system by using determinants, and that's what Cramer's rule is all about. But let's look at this concept here. This is called the adjoint theorem. If A is invertible, then A inverse, the inverse of the matrix, is the adjoint of A divided by its determinant. Let's look at some examples. Decide whether the given matrix is invertible. If so, use the adjoint method to find the so-called inverse. Excuse me. I need to state it here. I don't see it in my notes. Let me put it here. This theorem says that if the determinant of a matrix, a square matrix, is not equal to 0, then the matrix is invertible. Matter of fact, it's if and only if, and let me state that. A square matrix is invertible if and only if the determinant of the matrix is not equal to 0. So a square matrix is invertible. If it is invertible, then automatically the determinant is not equal to 0. Well, it might be difficult to determine if the matrix is invertible. Well, just look at the determinant. If the determinant is not equal to 0, then we said that the matrix is invertible, and that's what I'm doing here. So here, decide whether the given matrix is invertible. If so, then use the adjoint method to find the inverse. If the determinant is equal to 0, then you stop and you say that A inverse does not exist. And this, by the way, this theorem that I put here is added to the monster theorem. Let's see. Now I put the answers there, but let's work it out. First, we want to find the determinant of A. I'm going to solve for this determinant by using cofactor expansion along the second row. And so the permutation sign would be a negative here. So this is going to be a negative times that negative 1. I delete its row and column. So I have 5, 5, 4, and 3. And then it's a plus sign for this permutation sign, but it's already there a negative 1, so plus this negative 1, delete its row and column, wrong row, so we have 2, 5, 2, and 3, so here we get 15 minus 20 minus 6 minus 10. So this is negative 5. Excuse me. And this is plus 4. So we get negative 1. So the determinant of A is not equal to 0. So the inverse exists, so I can proceed by trying to find the so-called adjoint of A. To find the adjoint, you first find the matrix of cofactors. So I'm gonna just do them in my head, and just remember that for the cofactors, it's the sign times the minor. And what signs we're talking about, is minus here, plus, minus. I'm backwards. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So for this first entry of the A11, I delete its row and column. So it becomes the determinant of the submatrix, which is -1 times, erase all these guys, it's confusing me. So here, the sign is positive out in front. This is -1 times 3 is -3 minus 0. I come to the next position on that row, and I go back to the matrix. I delete its row and column. Its sign ultimately would be a negative once I solve for that determinant. But here, this is -1 times 3 is -3 minus 0. So it's -3 times a 3, positive. Well, -3 times the -1 is +3. Come here to this position, delete this row and column. So this is -4 plus 2, so that's -2. The sign permutation change in the front is positive, so that doesn't change anything. I come to this position, delete its row and column, so this is 15 minus 20, so this is -5, and the sign here is negative, so this is +5. Come to this position, delete this row and column. So this is 6 minus 10 is -4. The sign out in front is positive, so it's just positive times -4 is -4. Come to this position, delete its row and column. This is 8 minus 10, so that's -2. But the sign is going to be negative in front, so that's -2 times a +2. We get -2 times -1 is +2. Come to this position, delete this row and column. You get 0 plus 5, which is +5. The sign here is positive out in the front, so that stays the +5. Come to this position, delete this row and column. This becomes 0, negative, then minus 5 is +5, but the sign here is negative for this position. Come to that last term there, delete its row and column. We get -2 plus 5. -2 plus 5 is 3, and the sign there is positive. So now the adjoint is the transpose of this matrix. So I'm going to transpose this guy. This is, the rows become columns. So this is -3, 3, -2, 5, -4, 2, 5, -5, and 3. And so now the inverse of A is 1 over the determinant of A times the adjoint of A. Well, the determinant was just -1, so we're just going to negate all these terms here, and we get the inverse. 3, -5, -5, -3, 4, 5, 2, -2, -3, and that's it. And hopefully that's what I have there, and it is. I didn't make any mistakes. I will finish this section on Wednesday, and I'll cover the review on Wednesday, and we'll take the test on Monday. Okay? Thank you. Make sure you bring in your exams with the corrections on that on Wednesday, as well. Thank you.